Hello. Hello,
Good
ma'am.
evening, sir.
Good evening, ma'am.
Sir, you can start, sir. Students will join.
Okay, ma'am. Good evening, all.
Good evening, sir.
Yes. So we were learning about the colligative properties. Last class, we did one of the colligative property, that is relative lowering of vapor pressure. Now, the second colligative property, we started with osmotic pressure. Osmosis and osmotic pressure, I explained in the last class. So anyways, we will try to understand again the definition of osmosis and osmotic pressure, all that. Then we'll continue with the topic today. We'll have to finish osmosis, osmotic pressure today. Now, what is osmosis? Now I explained it using a Tissel funnel. We will explain it in the different format today. Now we will take a container like this, and this is partitioned by a semi-permeable membrane. I told you what is semi-permeable membrane. A membrane which allows only the solvent particles to move is called as what? Semi-permeable membrane. Now here we have a solution. Here we have a solution. Here we have only a solvent, a pure solvent we have. And there is an opening here like this. There's an opening, and we will erase this part of it. Oh, right. There's an opening like this, and also a mark or a graduated scale is here. Now what happens is, this is a solution and this is a pure solvent. Now solution can be considered to be concentrated and solvent can be considered to be dilute. Now if you take NaCl, 1 molar NaCl, and I take the water, water also contains some salts, but the concentration of salt will be less here in the solvent, pure water. So what happens is, if you leave for some times, the solvent particles will move from the region of lower concentration into the region of higher concentration through what? Semi-permeable membrane. That process is called as osmosis. This osmosis was first observed by a scientist named Abbe Nollet. The scientist who observed osmosis first was Abbe Nollet. What is this osmosis? The flow of solvent from pure solvent or from solution of lower concentration into a solution of higher concentration through a semi-permeable membrane is called as osmosis. Now, what is this osmosis? Movement of solvent particles from a region of lower concentration to higher concentration, or from pure solvent to that of solution through a semi-permeable membrane is called as osmosis. Now we will learn what is osmotic pressure. I defined osmotic pressure also last class, but anyways, before learning the osmotic pressure, we will learn exoosmosis and endoosmosis. What is this exoosmosis? If you have a cell here, it's a cell, any cell for that matter, a cell, and this cell also has some fluid inside. All right, and there are some fluid outside also. Now, if the fluid flows from inside the cell to the outside, if there is an outward flow of water from the cell containing an aqueous solution through a semi-permeable membrane, is called as exoosmosis. See, the outward osmotic flow of water from a cell containing aqueous solution through a semi-permeable membrane is called as what? Exoosmosis. What is exoosmosis? From the cell, if it flows outside. Now, if you keep a cell, or maybe the example they've given is grape. If you place a grape in NaCl, G-R-A-P, grape in NaCl solution. Assume this is grapes and this is what NaCl solution. What happens? Whatever the water present in the grapes will come out of the grapes. Then that process will be called as what? Exoosmosis. In case of exoosmosis, the grapes will what? Shrink, or the cell, if you take, it will shrink. If the water or any liquid from the cell flows out of the cell, what happens? The cell will shrink. That process is called as endoosmosis. Now, exoosmosis, when we say, see, this is a normal grapes. In endoosmosis, if you keep a raisin is a dried grapes. Raisin, if you keep in water, what happens? Water flows inside what? The grapes. The raisin will get what? Swells. The grapes get swollen. So that process is called as endoosmosis. The inward flow of water into the cell containing an aqueous solution of solution through a semi-permeable membrane is called as endoosmosis. An egg placed in water swells up due to endoosmosis. Likewise, a raisin placed in water also what? Swells. So this is called as endoosmosis. Did you understand these two terms? Students,
Yes, sir.
Yes. Now, I hope that you understood osmosis, exoosmosis, as well as endoosmosis. Reverse osmosis is a regular question for you. Reverse osmosis. We will learn reverse osmosis in a minute. Now, we will learn what is osmotic pressure. What is osmotic pressure? Now, this is a container, and this is a semi-permeable membrane. And here we have only solvent, pure solvent, and here we have a solution. Here we have a solution. Now what will happen? Now this is a graduated. What happens? Now the solvent particle will move from what? The solvent into what? The solution. This process is called as osmosis. Now what we will do is, we will keep a piston here fixed. This is a piston which is fixed. It is not movable. So when this piston is fixed, what happens? The solvent particles will not enter what? The solution. So that means you are applying the external pressure in order to prevent the movement of solvent particle from the region of lower concentration to the region of higher concentration. This process, or this external pressure, what we apply, this external pressure applied to prevent osmotic pressure. It's called osmotic pressure, is represented by letter pi. Now, do you understand what is osmotic pressure? The external pressure applied in order to prevent osmosis. See, we are fixing a piston here. I mean, this piston is not movable. Therefore, what happens? The pressure which is applied externally, it prevents the flow of solvent particle from a region of lower concentration to higher concentration. That's called as what? Osmotic pressure. Followed with this?
Yes, sir.
Now, we will talk about reverse osmosis. What is this reverse osmosis? The external pressure what we apply, if we apply a higher pressure, what happens? This piston will be moving down. When this piston moves down, higher pressure, what happens? Water or the solvent from the region of higher concentration flows into the region of lower concentration. Now, RO water filters, you would have heard of it. So the salt water will be there. They'll apply excess pressure. What happens? Only the solvent particle, pure water, will move into what? Into a solvent state. From the solution, only the water will pass through a semi-permeable membrane. That's called as what? Reverse osmosis. What is this reverse osmosis? If a pressure higher than the osmotic pressure we told, The external pressure applied in order to prevent osmosis is called as osmotic pressure. That's pi. If the extra pressure, if we apply, which is greater than osmotic pressure, I'm just showing it as P greater than pi. P is the excess pressure. Pi is the osmotic pressure. The excess pressure applied greater than osmotic pressure, what happens is the solvent will flow from the solution into pure solvent. That means the solvent will start flowing from the region of higher concentration into region of lower concentration through a semi-permeable membrane. Since here the flow of solvent is in the reverse direction to that observed in the usual osmosis, this process is called as what? Reverse osmosis. What is osmosis? Flow of solvent particles from the region of lower concentration to higher concentration. Now, the pressure applied to prevent osmosis is called as osmotic pressure. If you apply excess pressure than the osmotic pressure, or if you apply pressure greater than the osmotic pressure, the solvent will move from the region of higher concentration to the region of lower concentration. It's opposite of what? Osmosis. Therefore, it's called as what? Reverse osmosis. Nowadays, we have RO, a water purifier. So all water purifier is based on this principle only, reverse osmosis. All right. Did you understand what is reverse osmosis? It's an important question for your 12th standard exam. Did you follow?
Yes, sir.
Yes. Now, coming to the difference between osmosis and diffusion. Osmosis is movement of solvent molecules, only the solvent molecules. Diffusion is a movement of solute molecules. Molecules from the flow move from the region of lower concentration to the region of higher concentration. Diffusion, molecule move from a higher concentration to higher concentration solute to the region of lower concentration. It occurs only across a semi-permeable membrane. Osmosis occur only across a semi-permeable membrane. Diffusion don't require. Example, shrinking of potato slice when kept in concentrated sucrose solution. Example, spreading of ink when drop of it is put in a glass water. So diffusion and osmosis is quite opposite. So in case of osmosis, movement of solvent molecules. In case of diffusion, movement of solute molecules. In case of osmosis, molecules move from region of lower concentration to region of higher concentration. In case of diffusion, molecules move from the region of higher concentration to the region of lower concentration. Osmosis definitely requires a semi-permeable membrane, but diffusion don't require a semi-permeable membrane. Example, they have given shrinking of potato slice when kept in a concentrated sucrose solution. You can give an example, raisin in water, all that you can give. All right. And diffusion is spreading of ink. If you put a drop of ink in a container of water, what happened? The ink gets completely spread in water. That process is called as diffusion. Now, we defined what is osmotic pressure. There are many ways of defining osmotic pressure. We will define osmotic pressure again, and we'll learn with the formulas and work out some of the problems based on osmotic pressure. Now, osmotic pressure of a solution at a particular temperature may be defined as excess hydrostatic pressure that builds up when the solution is separated from solvent by semi-permeable membrane. It is denoted by pi. It's a complex definition. Okay, osmotic pressure of a solution at a particular temperature may be defined as excess hydrostatic pressure that builds up when the solution is separated from solvent by semi-permeable membrane. Or osmotic pressure may be defined as excess pressure which must be applied on the solution in order to prevent the flow of solvent into solution through semi-permeable membrane. This is what we define. This is what we define. And one more method of definition is there. Osmotic pressure may be defined as the excess pressure which must be applied to a solution in order to prevent the flow of solvent into a solution through a semi-permeable membrane. It's the same thing. Both the same thing. Or maybe in order to prevent, you can write osmosis. In order to prevent osmosis, you can finish off it in one word. Instead of writing the flow of solvent into solution through semi-permeable membrane, you can say prevent osmosis. The external pressure applied or the excess pressure applied, which must, in order to prevent the flow of solvent particles into a solution through a semi-permeable membrane, is called as osmotic pressure. What are the methods of measuring osmotic pressure? Measurements of osmotic pressure. The following methods are used for the measurement of osmotic pressure, in which you do not have any of these in your syllabus for 12th standard. Only for the competitive exam, you can just remember the names. Pfeffer's method, Morse and Fraser's method, and Berkeley and Hartley's method. This is important. Berkeley's and Hartley's method. Because in 11 to 12th standard, they will talk about this Berkeley's and Hartley's method. They will just mention it. And Townsend's negative pressure method, De Vries' plasmolytic method. There are 5 methods, but remember one method. This name you should remember. For a competitive exams, you should remember this method, Berkeley's and Hartley's method, in order to measure the osmotic pressure. Now, what is the function of learning colligative properties? The important function of learning colligative properties is to determine the molecular mass. So likewise, even using osmotic pressure, we can determine the molecular mass of a non-volatile solute. So we learned it in the previous class, that is relative lowering of vapor pressure. Using relative lowering of vapor pressure, you can determine the molecular mass of a non-volatile solute. Likewise, even using osmotic pressure, we can determine the molecular mass of a non-volatile solute. How can we determine the molecular mass of a non-volatile solute? We need to understand. Osmotic pressure is a colligative property which depends only on the number of solute particles, not on the nature of the solute particle. For a given solvent, the osmotic pressure depends only on the molar concentration. Molar concentration is nothing but what? Number of particles. Number of particles. So osmotic pressure depends only upon the molar concentration of the solute, but does not depend on its nature. The following relation relates osmotic pressure to number of moles. According to Boyle's Van't-Hoff law. Boyle's law is for gas. I told you gas and dilute solution as an analogy. Therefore, we call it as Boyle-Van't-Hoff law. At constant temperature, osmotic pressure is directly proportional to concentration. Here they're clearly given, for a given solvent, the osmotic pressure depends only upon the molar concentration of the solute. Only upon the molar concentration of the solute means number of particles, I told you. So osmotic pressure is directly proportional to concentration. According to Gay-Lussac's Van't-Hoff law, at constant temperature, osmotic pressure is directly proportional to temperature. This is marked as 1, and osmotic pressure is directly proportional to temperature. This is marked as 2. So according to Gay-Lussac's law, osmotic pressure is directly proportional to temperature. Now, if both the laws are combined, on combining both the laws, what happens? Combining both laws, we can write, equating both the laws otherwise, pi is directly proportional to Ct. Pi is osmotic pressure, which is directly proportional to concentration, and osmotic pressure is also directly proportional to temperature. Now, if you remove this R, we give a proportionality constant. It's called as what? R. If we remove this proportionality sign, we give a proportionality constant R. What is this R? This R is not universal gas constant. It is called as solution constant. In this chapter, it is called as what? Solution constant. It also has a value 8.314 joules per mole per Kelvin, or 0.08314, the unit, So R is called a solution constant here. So pi is directly proportional to Ct, or pi is equal to C into R into T, or you can write pi is what is equal to R into Ct. This is anyways you can write. Now, what is C? Concentration. Concentration, molarity, if you take number of moles of solute divided by volume. Concentration is written as C is equal to N by V. So in place of C, we're substituting number of moles by V. Because we know C is equal to N by E. N is number of moles and V is what? Volume. So what is N? N, we know number of moles is calculated by the formula W, weight. Number of moles is what? Weight by molecular weight. Weight in grams divided by molecular mass. This is how you calculate the number of moles. So, or else we can write it as W by M. So substituting for N, W by M here in this equation, N, if you substitute as W by M, then the equation reduces to pi is equal to W by M into RT by V. So this is the formula to calculate the osmotic pressure. Now, not only this formula you should remember 1, 2, 3, 4, and 5. These 5 formulas you have to remember in case of osmotic pressure so that we can work out some of the problems. I hope this is simple derivation. You followed with this?
Yes, sir.
Yes. So pi v is equal to what's it, pi, or else we can write this equation also as what? Pi v is equal to nRT. You know that PV is equal to RT. PV is equal to nRT, ideal gas equation in first PUC you would have learned, 11th standard. So here also likewise we have cross multiply this. So we get pi v is equal to nRT. So all these formulas you should remember. C is called as concentration of the solution in moles per liter. R is a solution constant here. You should not mention it as gas constant. Solution constant, but it has the same value as gas constant. N stands for number of moles of solute. V is the volume of the solution. M is the molecular mass of the solute. W is the weight of solute. Based on this, you can work out some of the problems later today. Conditions for getting accurate value of molecular mass. What are the conditions for getting the accurate value of molecular mass? Firstly, the solute must be non-volatile. The solute must be non-volatile. The solution must be dilute. The solution should not undergo dissociation nor association. So this is the main condition. This is the main condition. Any solute, non-volatile solute. The second condition is this: the solute should not undergo dissociation or it should not undergo association. Right? So this is with respect to condition of getting accurate molecular mass. These formulas you should remember. These two I will not talk about it now because these two, boiling point and freezing point, we have not spoken, but we have spoken relative lowering of vapor pressure. See, relation of osmotic pressure with different colligative properties. Osmotic pressure is related to relative lowering of vapor pressure, elevation and boiling point, depression and freezing point, according to the following relation. Remember this formula now. Now, this is what? Relative lowering of vapor pressure. P naught minus P divided by P naught. We have worked problems in the previous class also, and we have derived this equation also. So, pi is equal to P naught minus P divided by P naught into D into RT by M. D is the density. D is the density. These two we will learn after we learn, after these two formulas we'll concentrate after we learn the elevation and boiling point and depression and freezing point. Now, this is density, and these two we have not learned. Elevation constant and depression constant we will learn after learning the other two colligative properties. Now, this is again important. What is this? This is isotonic, hypertonic, hypotonic solution. Now, what is this isotonic? Isotonic is also called as isoosmotic solution. Iso stands for same. Isoosmotic solution. When we say isoosmotic solution, if two solutions of different substances having same osmotic pressure at same temperature, they are known as isotonic solution. What do you mean by isotonic solution? Two different solutions having same osmotic pressure at same temperature is known as isotonic solution. This is important. Definition they will ask you. What is isotonic solution? A solution or two different solutions having same osmotic pressure at given temperature is known as osmotic pressure. Now, for an example, assume that I have a container like this. This is a semi-permeable membrane. I have glucose solution here, 0.1 molar glucose solution, and I have 0.1 molar sucrose solution. See, the number of molecules in both the cases is same. So that means glucose also will exert same pressure as what? Sucrose. Therefore, what happens? Osmosis will not take place because the osmotic pressure exerted by both is same. Therefore, the solvent will not flow from sucrose to glucose or from what? Glucose to sucrose. The solution will not, solvent will not flow. So those kind of solutions are called as isotonic solutions. Now, for an example, if a person meets with an accident, if a person has to be given a glucose immediately, you would have heard of in the hospitals, they give saline solution. Saline solution is around 0.93% sodium chloride solution. The saline solution, when they inject in the vein, the pressure exerted by the saline solution and the pressure in the blood cells will be what? The same. Isotonic. It becomes isotonic. That is what it means when two different solutions having same osmotic pressure at similar temperature are called as isotonic solutions. Now, isotonic solutions, see this formula also you should remember. For isotonic solution, P1 is equal to P2. This is the primary condition. So osmotic pressure of one solution should be equal to the osmotic pressure of other solution. And also you should understand when osmotic pressure is same, what happens is we will know that the concentration C1 is also equal to C2. C1 is also equal to C2 because colligative property depends only on the number of particles. Therefore, concentration remains same. So concentration we can write as what? N by V, number of moles divided by volume. C1, therefore N1 by V1, C2, N2 by V2. So this formula also you should remember. For isotonic solution, N1 by V1 is equal to N2 by V2. This is the there was some issue with the network, I believe. Students, are you there?
Yes, sir.
Yes, yes. You can see the screen, right? You can see the screen, right?
No, sir, it's not visible.
I don't know what happened suddenly. Again, yeah, it's not visible. Right.
No,
Now,
Yes,
now.
sir. Now
Yeah,
it's
yeah,
visible.
yeah. I don't know. There was some network issue, I believe, because it's raining here. Now, this formula holds good only for those solute which neither possesses the tendency to get associated or dissociate. So this is the molecule. Associate means combination of molecule. Dissociation means breaking of molecule. Now, urea and glucose are isotonic. Urea will not undergo dissociation, neither glucose will undergo dissociation. So urea and glucose are isotonic. Then pi 1 is equal to pi 2. Osmotic pressure of urea is equal to osmotic pressure of glucose, and C1 is equal to C2. That means concentration of glucose will be equal to concentration of glucose. Urea and sodium chloride are not isotonic. Why? Because sodium chloride will dissociate. Sodium chloride dissociates, it becomes two particles. One molecule of sodium chloride becomes two particles, Na plus and Cl minus. The number of particles changes. But colligative property depends only on the number of particles. Therefore, what happens? Urea and sodium chloride will not form an isotonic solution. Even though osmotic pressure also will not be same, concentration also will not be same. So likewise, next we have urea and benzoic acid. They undergo association. Any carboxylic acid for that matter, they will associate. And isotonic, urea and benzoic acid are isotonic, then pi is equal to pi 2, but osmotic pressure is same, but the concentration is not equal to same. Here also in this case, sorry, I made a mistake. Here also the osmotic pressure is equal, but the concentration is not same because they undergo association. Hypertonic and hypotonic solution. What is this hypertonic and hypotonic solution? Hypertonic solution, the solution which has more osmotic pressure than other solution is called as hypertonic solution. And a solution which has lesser osmotic pressure than the other solution is called as hypotonic solution. Now, for an example, if I have two solutions here the osmotic pressure is pi 2 and here the osmotic pressure is pi 1. If pi 1 is greater than pi 2, then pi 1, this solution will be called as what? Hypertonic. And here, since pi2 is lesser, this will be called as what? Hypotonic. Did you understand? A solution which has more osmotic pressure than the other is called as hypertonic. A solution which has lesser osmotic pressure than the other is called as hypotonic. All right. Now, the flow of solvent is always from lower osmotic pressure to higher osmotic pressure. Lower osmotic pressure to higher osmotic pressure. That is from hypotonic to hypertonic. That means flow of solvent particle is from the region of lower concentration to higher concentration. That is hypotonic solution to hypertonic solution. Followed with this hypotonic and hypertonic.
Yes, sir.
Students, yes. So if that's the case, we will try to work out some of the problems based on this osmotic pressure. We'll have to learn the laws of osmotic pressure, that is Van 't Hoff's law. We will learn Van 't Hoff's law, all that little later. We will try to solve few problems based on osmotic pressure. Now, the first one is calculate the osmotic pressure in pascals. Calculate the osmotic pressure in pascals. Pascal is one of the units, one of the method of expressing the pressure. It's a unit to express pressure exerted by a solution by dissolving 1 gram of polymer of molar mass 185,000, 1,85,000, the molecular mass of a polymer, in 400 ml of water at 37 degrees Celsius. Now, what is given in the question? The mass of solute they were given. Mass of solute. What is the mass of solute? What's the mass of solute? They've given us 1 gram. And also they've given molecular mass or molar mass of that solute. What is the molecular mass or molar mass of the solute? Molar mass of the solute is 1,85,000. 1,85,000 gram per mole. Gram per mole. And also they've given volume of the solution. 450 ml they've given. 450 ml converted into liters, it will be 0.45 liters. 450 ml is what? 0.45 liters, yes or no?
Yes,
or
sir.
no? Yeah, temperature they have given 37 degrees Celsius, converted into Kelvin scale. What's the conversion factor? 37 plus 273. That will be equal to 310 Kelvin. Good. That will be 310 Kelvin. Now, R, you should know solution constant. It is 8.314 kilopascal per liter, kilopascal liter per Kelvin. This Kelvin per mole. This is the unit for R. So this can be converted into pascals. So it will be 8.314 into 10 to the power 3 pascals liter per Kelvin per mole. So kilopascal is here. 1 kilo is what? 10 to the power 3, converted into pascals. Now, what is the question they're asking? They're asking you to calculate the osmotic pressure. They're asking you to calculate the osmotic pressure. What is the formula we know? We know that osmotic pressure pi is equal to C into R into T. We learned C into R into T. Pi is proportional to C into T. If you remove the proportionality constant, we give R as a constant, solution constant. So we can write pi is equal to N by V into RT. What is N? N stands for number of moles. Now, what is number of moles? We have not given the number of moles is weight in grams by molecular mass. Now, what is weight? They have given 1. Molecular mass is 1,85,000. So that's nothing but the number of moles. So what will be pi? Substituting, pi will be equal to 1 by 1,85,000 divided into, what's the volume? Volume is 0.45 liters. And the the solution constant, it is 8.314 into 10 to the power 3. And what is the temperature? Temperature is 310 Kelvin. On simplification, it's a lengthy problem. This is simplification will take time. On simplification, we will get this as 30.96 pascals. 30.96 pascals. So the answer for this question is option B. Kindly go through this problem. It's a simple problem. The formula what we have used is this. The formula what we've used is pi is equal to C into R into T. What is C? C is concentration. How do you calculate concentration? Concentration is given by the formula number of moles by volume. Because we know, maybe we can write here, we know that C is nothing but N by V. What is N? Number of moles. V is volume. So number of moles, how do you calculate? Weight in grams by molecular mass. Substituting and simplification. So direct substitution and simplification, you will get the answer to be 30.96 Pascal. Please remember, when they ask you the units are given in Pascal, you have to take R as 8.314 into 10 to the power 3. In other units, you will take R in a different way. Whenever they have given the pressure, osmotic pressure in terms of pascals, you have to take R as 8.314 into 10 to the power 3 Pascal liter per Kelvin per mole. Clear with this? Simple problem? Yes? Yeah. The next question. At 300 Kelvin, 36 grams of glucose. At 300 Kelvin, 36 grams of glucose present per liter in its solution, and has an osmotic pressure 4.98 bar. If the osmotic pressure of the solution is 1.52 bar at the same temperature, what would be its concentration? What would be its concentration? What is given? They have given the temperature to be 300 Kelvin. They have given pi 1, two osmotic pressures they have given. So we'll take pi 1 to be 4.98 bar. And they have given the molecular mass, or mass of glucose. Mass of glucose, they have given to be 36 grams. And we should know the molecular weight of glucose. The molecular weight of glucose, I told you in the last class also, it is 180. And they have given osmotic pressure, pi 2, they have given us 1.52 bar. And what is that they're asking? They're asking you to calculate the concentration. Calculate the concentration. That is, they're asking you to calculate C. So what's the formula? We know that concentration, we know it is 36 divided by number of moles by 180 into R, and the temperature is 300. We'll mark this as equation number 1. And the second osmotic pressure they've given us 1.52. 1.52 is equal to C into R into temperature is 300. This is equation number 2. So dividing equation 2 by 1, dividing equation 2 by 1, what you will get? We'll get 1.52 divided by 4.98. That will be equal to C into R into 300 divided by 36 by 180 into what? R into 300. So on simplification, you will get this value as 0.31. 0.31 is equal to 5C. This simplification is 5C. R and R gets cancelled. 300 will get cancelled. 180 by 36 is 5. Therefore, you get 0.31 is equal to 5C. Or C is equal to 0.31 divided by 5. So the answer for that is 0.062 molar. The answer what we get is 0.062 molar. So the answer option is option A. So the only formula what we use is pi is equal to C into R into T. Since they have given two osmotic pressure, so for the first osmotic pressure, 4.98, we know the concentration because they've given 36 grams and the molecular mass also we know. So R into 300. For the second osmotic pressure, it's 1.52. We don't know the concentration. They are asking if the question C, if the osmotic pressure of the solution is 1.52 bar, at the same time, what would be its concentration? So they've given the osmotic pressure in the second case. We don't know the concentration. They're asking us to find the concentration. Therefore, equation 2 divided by equation 1, on simplification, we get concentration as 0.31 divided by 5. And the answer we get is 0.062 molar. Hence, the answer for this question is option 1. Did you follow this? Students?
Yes, sir.
Yes. Now, the next question. Determine the osmotic pressure of a solution prepared by dissolving 25 milligrams of potassium sulfate in 2 liters of water at 25 degrees Celsius, assuming that it is completely dissociated. So potassium sulfate, K2SO4, potassium sulfate is dissolved. What is given? The solute is potassium sulfate, which is dissolved. How much of potassium sulfate is dissolved? 25 milligrams. This 25 milligrams is 0.025 grams. You should know how to convert milligrams into grams. For the divide by 1,000, you will get what? 0.025. Now, what's given? Volume of the solution. They've given volume of the solution to be 2 liters. And they've given temperature to be 25 degrees Celsius. It is nothing but 25 plus 273. That is 298 Kelvin. 298 Kelvin. Now, to find the osmotic pressure, what is that we're supposed to find? We're supposed to find the osmotic pressure because they're asking, determine osmotic pressure. Now, we know that pi is equal to C into R into T. And also remember one more formula I'm introducing here. Pi is equal to I into C into R into T. I is called as Van 't Hoff factor. I is called as Van 't Hoff factor. What is Van 't Hoff factor? We will learn. So that will be equal to what now? I into C is what? N by V into R into T. Or that is equal to I is equal to I into W by M. Because number of moles, N is equal to what? W by M. So W by M into 1 by V into RT. This is into I into W by M into 1 by V into RT. This is the formula. Now you understand this. What is I? This K2SO4, it says completely dissociate. It will dissociate to form 2K plus and SO4 2 minus. It gives you how many ions? 3 ions. 2K plus and 1 sulfate ions. Therefore, I is 3. I is 3. Number of ions produced is I. Number of ions produced is I. And also you should know the molecular mass of potassium sulfate. The molecular mass of potassium sulfate is 174 gram per mole. Gram per mole. So with all this, you can substitute here. I is equal to 3. Weight, they have given us 0.025. And the molecular mass is 174 m. 1 by, what's the volume? 2 liters, 2. R here, it is not in pascals. You can see the pressure is given in terms of what? Atmospheres. When the pressure is given in terms of atmosphere, you have to take the R value as 0.082. You have to take the R value as 0.082 and temperature is 298. So in case of pascals, we took R value as 8.314 10 to the power 3 Pascal liter per Kelvin per mole. When the pressure is in terms of atmosphere, we should take the R value as in terms of like this, 0.082. So on simplification, we get the osmotic pressure to be 5.27 into 10 to the power minus 3 atmospheres. Therefore, the answer for this question is option A. It's a simple formula, and we have introduced a term called as I. I is called as Van 't Hoff factor. This I stands for number of ions produced. Number of ions produced. I will write here. I stands for number of ions produced. So the number of ions produced by potassium sulfate is 3. Therefore, I, we take it as 3. I hope you followed with this problem.
Yes, sir.
Yes. Oh my God. Next problem. A cane sugar solution has an osmotic pressure 2.46 atmosphere at 300 Kelvin. What is the strength of the solution? What is the strength of a cane sugar, sugar cane or cane sugar, sucrose? Sucrose contains an osmotic pressure of 2.46 atmosphere at 300 Kelvin. What's the strength? We know that PV is equal to nRT, or we can write this also as pi v is equal to nRT. We can write pi is equal to n by VRT. We learned this equation. We learned this equation today. Pi is equal to n by VRT. That is equal to what? CRT. N by V is nothing but concentration, CRT. So what will be C now? C will be pi by RT. Or simply we can take pi is equal to CRT. What is C? C is equal to pi by RT. Same thing. So pi they've given 2.46. R, it is 0. See, again, the pressure they've given in terms of atmosphere. So R, you will take it as what? 0.82. And what's the temperature? Temperature they've given 300 Kelvin. So substituting and simplifying, you will get the answer to be 0.1 molar. The answer for this question is option A, 0.1 molar. Followed with this, the simple problems. In case of osmotic pressure, the problems what we're doing are simple. You should know the substitution and the units. Next problem. What is the osmotic pressure of 12% sugar? So not sugar, 12% solution of cane sugar. Cane sugar is sucrose, molecular mass is 342 at 17 degrees Celsius. What is given? What is given? The 12% they say. What do you mean by 12%? 12 grams of sugar dissolved in 100 ml of water. Weight by volume, 12% when we say 12 grams of sugar in 100 ml of water. Thus, 342 grams of sugar is dissolved in what liters? So it will be 342 into 100 divided by 12. 12, that will be into what? Into 1000. Because 1 liter is 1000 ml. So you will get 2.85 liters. So 2.85 liters. 2.85 liters. So we know that pi v is equal to RT, or pi is equal to RT by V. So that's nothing but 0.0821 into 290. 290. Temperatures, yeah, 273 plus 70, that is 290 temperature. And volume, they've given us 2.85. On simplification, you will get 8.35 atmospheres. 8.35 atmosphere. Hence, the answer for this question is option B. Go for the next problem. A solution containing 8.6 grams of urea in 1 liter was found to be isotonic with 0.5% weight per volume solution of an organic non-volatile solution, the molecular mass of the latter. See, a solution containing 8.6 grams of urea in 1 liter was found to be isotonic with 0.5% solution of organic non-volatile solution, the molecular mass of. We found out N1 by V1 is equal to N2 by V2. We learned the relation, or we learned it as W1 by M1 into V1 is equal to W2 by M2 into V2. We found out, we used this formula. Now this will consider it for urea, and this will consider it for organic compound. Now they're asking molecular mass of the latter. That means they're asking you to calculate M2. They're asking you to calculate M2. What is given? Weight of urea is 8.6. Molecular mass of urea is 60. Remember, molecular mass of urea is 60. And what's that they've given? Volume, 1 liter. 1 liter is 1000 ml, 1000. That will be equal to weight of the organic liquid. It's 0.5. 0.5% they've given. So it's 0.5 gram divided by M2 we are supposed to find. And V2 is also in 1 liter. 1 liter. So therefore, on simplification, we'll get M2 to be 34.89. So molecular mass of this will be 34.89. Did you follow? Students, you follow?
Yes, sir.
Yes. All right. The next question. Where is that? See, these are different types of questions in osmotic pressure we learned. In another 2 classes, maybe we should finish this chapter solutions in detail. So a few more questions we'll see. The osmotic pressure of a solution can be increased by, increasing the volume, increasing the number of solute molecules, decreasing the temperature, removing the semi-permeable membrane. Any colligative property is directly proportional to the number of solute particles, remember. So colligative property is directly proportional to number of solute particles. We know that pi is equal to C into RT, concentration. We learned concentration stands for number of particles, or else we can write pi is directly proportional to C also, we learned. So that means by increasing the number of solute molecules, osmotic pressure can be increased. Therefore, the answer for this question is option 1. Now see this problem based on isotonic. A 5% solution of cane sugar, 342 molecular mass, is isotonic with 1% solution of substance X. The molecular mass of X is 5% solution, 5 divided by 342. The molecular mass of cane sugar is 342 into 1000 divided by 100. What is this? 5 grams in 100 ml. So 342 in 1000 ml. That is this. That will be equal to 1 by X, 1% solution, into 1000 by 100. So on simplification, the value for X, we will get it as 342 by 5. This 342 goes here and 5 comes here. So it will be 68.4. 68.4. So you should know isotonic solutions means the osmotic pressure will be equal to both. Or else we can write pi 1 is equal to pi 2. What is pi 1? C into RT. C1 into RT. Here it will be what? C2 into RT. So C1 is what? 5 by 42. 342. Here C2 is 1 by X, because 1% they've given. We don't know what is X. We're supposed to find. And this is from 1 mole. So 1000 by 100. Percentage is in terms of 100. Therefore, 1000 by 100, 1000 by 100. You'll get 68.4. 68.4. Did you follow? Yes?
Yes, sir.
So 1 or 2 more problems we will see, and then we can stop with this class today. During osmosis, flow of water through semi-permeable membranes from solution having higher concentration only. Sorry. Students, can you see the screen?
Yes, sir, it's visible.
Okay, solution having higher concentration only from both the sides of semi-permeable membrane with equal flow rates, from both sides of semi-permeable membrane with unequal flow rates, from solution having lower concentration only. So flow of water through a semi-permeable membrane from a solution having lower concentration. So movement of solvent particle from a region of lower concentration to a region of higher concentration is called as osmotic pressure. Therefore, the answer for this question is option D. Now we'll look into this question. A solution containing 10 grams per decimeter cube of urea, molecular mass of urea is 60 gram per mole, is isotonic with 5% solution of non-volatile solute. The molecular mass of the non-volatile solute is 10 grams of urea is isotonic with 5% solution. So what does it mean? 10 grams of urea is isotonic with 5% solution of non-volatile solute. It means osmosis is not possible. 10 grams of urea, 10 grams per decimeter cube of urea is isotonic with 5% of the solution. See, when we say there's isotonic, there is no movement of what? Solvent particles. No osmosis possible. No osmosis possible. Maybe I will write for you to understand. 10 gram per decimeter cube of urea is isotonic with 5% solution of the non-volatile solute. Hence, between these two solutions, Osmosis is not possible. Osmosis is not possible. Because they have same as osmotic pressure they have. So molar concentration of them will be equal. So their molar concentration is equal. Their molar concentration should be equal. Number of particles should be equal. Thus, we can write, thus, molar concentration of urea is 10 divided by 60. That will be equal to 1 by 6. Because 10 grams they give, molecular mass of urea is 60. That is 1 by 6 molar. Now, molar concentration of 5% non-volatile solute. So 5% non-volatile solute. When we say 5%, 5 grams per 100 ml or 50 grams per decimeter cube. Here they've given in terms of decimeter cube. That's why we have to convert this. 5% means 5 grams per 100 ml. But it's for a liter, it's 50 grams per decimeter cube. Divided by molecular mass. That will be equal to 1 by, if I equate both, since they are isotonic, this will mark it as equation number 1. This will mark it as equation number 2. Since they are isotonic, what happens? 1 by 6 is equal to 50 by molecular mass. So, or else molecular mass will be equal to 300. 6 into 50, that is 300 gram per mole. Therefore, the answer for this question is option B. Did you understand this question? Did you follow us? It's an isotonic solution. Since this is an isotonic solution, what happens is there is no osmosis. So therefore, the concentration of both the solutions should be same. Based on that idea, we calculated the concentration of urea to be 1 by 6 molar. Concentration of 5% is 50 gram per decimeter cube of molecular mass. It's not 5 by molecular mass. If you take 5, it goes wrong. Because here they've given 10 gram per decimeter cube. So 5% you have to convert into a liter. So it becomes 50 grams per decimeter cube. Did you follow this?
Yes, sir.
Okay. We will stop the class now. We'll continue possibly tomorrow with the other colligative property. Ma'am, I'll stop the class.